This is lecture 17, example 1. There's actually no lecture 17 as of yet. Nothing new to say, give you time to catch up. And we're just going to do another timing example. This will probably be our last timing example. Maybe, I don't know. So here it is. This is the example. We have a fragment of code over here, and it's got some initial conditions up here, and the idea is to fill in this diagram below. Now, if you look at this thing, we're going to do a quick analysis of it. Everything looks like we got a load instruction there, so we got to we know that's going to be a 3-cycle instruction if we make it there. And we also have a conditional in here, so we just can't write these instructions down. We got to take them a few instructions at a time. So what you should be able to notice is what I designed the problem for is that is a push, and that is a pop, and you're going to actually see those instructions being executed, and that was kind of the whole point of this. Or not the whole point, but a major point in this. Okay, so I have this program written down on a piece of paper here, so I can reference it. Unfortunately, I can't get it on the paper, but I'm going to start writing that down as I know it. Add I. There's the adjustment of the stack pointer, and then it follows with a store word. And it follows by an XOR. We can just crank through these because we know it's going to actually happen. And there's the BEQ. And after the BEQ instruction, we don't know what happens. So this is the fetch, execute, fetch, execute, fetch. And we'll leave it at that. So the PC is given. The starting PC is going to be, what is the PC going to be? It's going to be the number associated with cat, which is B0. So 0xB0, we can fill that in. Next instruction is, of course, going to be 4 beyond that. That's going to be 0xB4. Next instruction is 4 beyond that, 0xB8. This one is 0xBC. Great. And then I have to stop because I don't know whether it takes to jump or not. So typically what we have is the PC write. It's always turns on in the last cycle before the next fetch cycle. It essentially means the execute cycle for most instructions, or the write back cycle for the load instructions. So we can crank these through. We know these are going to do that. Looking good. Reg write. Okay, so let's look at these instructions. This is an add I. We know the register is being written. This is a store word instruction, which is taking something from a register and storing it in memory. And that being the case, we don't need to write anything to the register. And this is an XOR instruction, which is writing something back to X8. And a BEQ instruction does not write the register. All right, we're looking good there. And here we go. We got a store instruction. This is the memory write, which is the data store. The add instruction doesn't use memory, but the store instruction does. So that in order to make the store work, we have to turn this memory write on, which we do in the execute cycle of the store instruction. And so that's XOR is not going to use memory. Certainly a branch instruction does not write anything to memory. Read enable 1 is always asserted during the fetch state. It's like a constant in our program, and so we can fill that in. Probably shouldn't even put it in the timing diagram because it's generally pretty much the same. And a read memory, and so this is the control that controls the synchronous memory read of data. That's not a memory read. That's a memory write. XOR is not a memory read. BEQ has nothing to do with memory. So looking good. And let's keep going down on this thing. So this one is, when it starts out, we don't really know what it is, but then it gets into ALU with the add. I know it's 0000. Generally speaking, you pick that up off the schematic diagram. There's a little table on the left. A store word is also going to be an add, because it's going to add the offset and the base register to form a effective address. So we're using the ALU to add, so it's 0000. XOR, once again, I got to pull that off the cheat sheet, and I don't have that one memorized. XOR 01000100. This, once again, it came off the schematic or the cheat sheet. And a BEQ instruction, we can go ahead and fill that in. Essentially, that's a don't care. We're not using the ALU for a branch, so we don't need to put anything there. So these are unknown. ALU, this is ALU source. A always chooses RS1. The store instruction also chooses RS1. The XOR instruction chooses RS1. BEQ here is it doesn't use the ALU, so that's a big don't care on that one. So we're getting there. And so ALU source B, this is kind of unknown. For the add immediate instruction, it chooses the immediate input to that lower mux, which is 01. For the store word instruction, it chooses, I think it chooses the S type. Got to check my manual here. It chooses the S type input to that lower mux, which is 10. XOR, this is going to be a register. It's going to choose the register input to that, which is 00. And BEQ here doesn't use the ALU, so that's a don't care. PC source. So PC source, whatever, we don't know that. But this is instruction. It's a normal instruction. Not a big deal. Chooses the 0 option of the PC mux. This is a normal instruction too, to 0, which is simply the advance by 4. And so this BEQ, it may choose 0, but it also may choose the branch option. We haven't really looked at it yet. So we're getting there. So read, write, select. This does write the register. And so I have to select the ALU result to go into the register. This store word here, what's a store word? It takes something from a register, read, write, select. So this is a don't care. I am taking something from a register and storing it in memory. I'm not writing anything to the register file, so that's a big don't care there. XOR, that is a normal type instruction, which is going to choose the ALU result to be written to the ALU to the reg file. So there's the 11 option, and this is the BEQ instruction. Essentially, the BEQ is not using the branch instructions. Don't use the register file. They're not writing to it, so that's a don't care. Okay, looking good. So we can actually come down here and say, don't know what these are. And for this one, this is the IO bus. Certainly we can fill that in, because we're not doing an input in this problem, so we don't need to worry about it. So the right, so this one is the result of the stack pointer. Might as well do the inputs to the stack pointer right first. So these are, we don't know what's coming out of the register. We don't really care, because what we're using is the thing that's coming out of the immediate generator. But we do know what's coming out of RS1, which is which is the stack pointer. So it's 0xf08, and the result is going to be subtracting 4 from that, which is going to be written to the register, which is 0xf04. Okay, that works good. Store word, it's storing x8 and into memory. It's essentially pushing it on the stack. So once again, we don't really know what's coming out of this register, so that's not going to be the issue here. Essentially, it's going to be 0 coming out of the immediate generator. So this, for the RS1, which is the stack pointer, it's our new stack pointer from this guy, which is 0xf04. It got adjusted by the last instruction, and the thing that's written to the reg file is nothing. We're not writing to the reg file. So this piece of data is also we don't care about it. Okay, moving right along. Up at this instruction here, we have what we're doing is exclusive ORing x8 and x9 and storing the result in x8. So once again, the RS2 actually does have a value in this thing. It's x9, which is 0x, a whole bunch of zeros there, but it's given in the problem as 5. The other piece of data to the other register is 0x, once again given in the problem as x. It's AA, which is completely contrived, and so the result of this XOR of these things is 0. Pretty exciting. All right. Next thing, we are looking at this branch instruction. So it's going to take the branch if x8 is equal to 0. So x8, here's your 0, and x8 is actually going to take the branch. No big surprise there. But so we'll go ahead and start up here, and it's going to branch to dog. It's going to branch to dog. Okay, so that's essentially we got to get the instructions. Got to get the number right. So this is BC. I'm counting it on my diagram. So it goes to C0, C4, C8, CC. CC is the address associated with dog. CC, and guess 0x CC, and that's going to be load word x8 0 SP, and so that's going to be our push instruction. It's going to be 3 cycles long, so I'll go ahead and mark that on this. And after that, we have an add immediate SP 4, which essentially adjusts the stack pointer. Okay, so PC right here, looking good. This is a 3-cycle instruction, and we're done with PC write. Reg write, load word is loading a value into the register. That means it's coming from memory into the register. Got to wait till it gets there, which is the last cycle, which is the write back cycle for that load instruction. Load instructions are 3 cycles, which means you'll see this in a second. We'll go ahead and finish this up. We're not reading memory anymore. And this is the same thing, but it has to take a little jog in it to get program instruction here. But this is what I'm interested in. Essentially in the execute cycle of a load instruction, since the memory is synchronous, I need to turn on the memory read. And I'm going to do it once again right in the execute cycle. So this is fetch, execute, write back, fetch, execute. And yeah, well, done with the top couple rows there. And let's move on to this thing. So load word is has to calculate an effective address. So I've got to get this right. It's actually a 3-cycle instruction. There's the add for to calculate the effective address. This is going to be a 0 to choose the top option, which is the register output option for the ALU. ALU source B is going to choose the I option, which is the immediate value, which is 0, 1. Load type instruction is a load is an I type instruction, so it chooses the I immediate value. PC source here, we've got to finish this up. This is actually very important. PC source took the jump, so the control unit sent out a 1, 0 to make sure that jump actually happened. Okay, so this one, loading a word, read write select. Oh, let's do the PC source. This is just a normal instruction. We can do that. Actually can finish this up. This is a normal instruction too, not a branch instruction. So the source for the load, it's loading something into a register. It's coming from memory, so I got to check my cheat sheet on that top register. The output of memory is the 2 option, so it's 1, 0. Looking good. And this instruction is normal instruction, which is writes to the register, so it's going to check and select 1, 1. ALU source for this instruction, add immediate. Top source is always needs to be 0 to select the RS1 output of the register file. ALU source B for this instruction, which is an add I. Add I is immediate instruction, so once again this is going to be a 0, 1. Okay, we're doing good there. Just a few more instructions, and so this branch instruction, the question is, what is it doing to register file? And it's not doing anything, so we're going to put some don't cares there. But for this instruction, we do have outputs coming out of the register file, which is going to be the things that are being compared and sent to the up to the branch condition generator. So these are both. This is the current value of x8 and x9, which are both 0 now because they got XOR'd. And done with that one. Load word here. We are loading something to the reg file. So I'm going to say I gotta get this right. And let's do the other ones first. It's easy. Okay, so RS1 is going to have the data. It's actually going to be there immediately. So we can put that in there. So this data. RS1 is the address 0x. It's the current stack pointer 0f04, and the notion is what's happening on the lower register, which is it's going to select load words and I-type instructions. So it's going to select the output of the immediate generator. So once again, we don't care what's coming out of the register. Looking good. And the issue here is this what goes in here. So this is a little bit special. So I would say initially we don't know what's there. After the instruction decodes itself, we know there's going to be an F04 there because that's one of the operands. But then after this, after it gets this, reads this value from memory. After it reads the value from memory, it's going to get a piece of data here, and so it's not F04. It's what's coming out of memory, and the thing that's in memory was the last thing we put in memory, which we pushed it there, which was the original value of x8, which is 0xAA. Okay, so that's better. That's looking good. There's our 0xAA. That's what's going to be loaded into a register. So it looks like we're done with that instruction. Next instruction here is what is it? And immediate. So what we're doing is subtracting the value from the register here, the stack pointer, we're adding 4 to it, not subtracting it. So the current value is F04, and the result after we add to it is going to be 0xF08, which essentially returns it back to its original value. And the RS1 in this instruction is F04, which is the old value. And lastly here in this guy is we don't know what's coming out of the register. The add immediate instruction is using the I-type value coming out of the immediate generator. Okay, so I will go ahead and call that done. Took a little bit of finagling here based on some issues here, but we're done.